Alright, so with this problem, I'm going to start with this one first. So I know that whenever I see LiCu, this is going to be one of the Gilman's reagents. So this unit here, these 3 carbons, I'll go ahead and number them. These carbons are going to be what we see in our product on the right-hand side. I also want to note this bond here. Notice how it kind of comes like out of the parentheses. That's intentional. This is signifying that like would be the new bond we see in the product. So we're only going to be adding these 3 carbons. We could ignore like that extra bond there. So where I see that pattern of those 3 carbons with the connection point being in the middle is right here. You can kind of see that pattern where it's those 3 carbons, and then our new connection point is right here. So I'll go ahead and highlight that too. So right now, it's looking like right at this carbon right here, that is our new connection point. So I'm gonna label it actually. So this is the connection point here. And the reason it's good to notice that is because then we could kind of work around and see what we can do here to draw the actual electrophile we started with in this box. So like I said, we know that the LiCu is going to do that 1,4 addition. And specifically, it does that 1,4 addition always on an enone. So I know I must have an enone in my product. My electrophile must be an enone. This is our product right here. I want to also say too that when we say 1,4 addition, the reason it's 1,4 is because we're starting with counting at the oxygen and then working our way down. And you can kind of see that's like the 4th spot that we added something. So it's kind of saying just like the spot we're adding to is that 4th carbon there. And coincidentally, it ends up at like where that new connection is, that bond I highlighted, at that 4 spot right here, at that new connection point. You don't need to even necessarily like do any arrows for this or like try to think what like the arrow pushing in general just would be. All you have to know is that alkene in our enone in the electrophile that we started with, I'm going to draw really quick the rest of the molecule. That alkene must have been in between the new connection point we see, the blue circle I put, and the carbon closest to your CO double bond. So just knowing that, identifying that new connection I highlighted, the carbon it connected to, and then the carbon adjacent to that right here, closest to the CO double bond. This right here then is where that alkene was in our enone starting material. And again, we knew it was an enone starting material because we knew this compound would do a 1,4 addition. 1,4 additions only can happen on enones. So knowing that, our starting material then would just, all you have to do is put a alkene there. And then again, we didn't add this unit yet here, those 3 carbons. So we can just go ahead and erase those 3 carbons and the bond in between that and the starting material. So we would end up getting something like this. Delete the circles. So that would be what our starting material would look like in this case. I'm going to just redraw that. So that would be the enone starting material. And again, this is kind of what we identified. We already identified the mechanism because we saw that the addition happened in the 4th spot away from the oxygen in the carbonyl. So we know that would just be 1,4 addition. here. And then for the next one, again, we're just going to identify that new bond. I'll highlight in blue like I did last time. And then the connection point of like the carbon we connected to that I circled in blue up here. So I am going to first identify that our starting material are organometallic in this first row. What this really is just the two carbons here with one of them having a negative charge. So I can just, it's gonna look a little weird, but one of those carbons would have a lone pair negative charge. So knowing that we have this type of pattern where there's those two carbons with one with a negative charge, I'm going to try to find that in my product. So I see one of them here, and I see one of them here. Now, technically, there are two answers you can get for this. You can consider one of these as the new addition, and then the other half of the molecule as being already there. Or you can consider both of them as the new addition, like two separate additions, as if like two additions happened twice, as if you had like snack, a leaving group left, and then second addition happened. But just because it's looking like the best or most simple thing to do here is just a single addition, we'll stick with that. So I'm just going to identify where these two carbons are in my product. Again, this is pretty symmetrical, so I could choose either side. I'll say these are the new ones here. And then my new bond, like I did last time, I highlighted that in blue. That would be here. And then that new carbon I connected to is just right here. Just like how I circled last time. So, having that connection point identified, I'm going to now go ahead and work backwards and draw what this electrophile could possibly be. A few things to note before we get into that are that any Li or BRMG organometallic is always going to attack any carbonyl in terms of like an aldehyde, ketone, or a ester. Or they can attack epoxides too. So these are the things that any of your organometallics can attack. So we need something that is either going to look like this and have that CO double bond, or something that is that triangle with that oxygen in the middle. So knowing that, and knowing that right now it looks like our single connection point for this one right here, you could see that this carbon right here had a single bond going from itself straight to that carbon 2 from our original organometallic. In this case, it looks like I should have probably numbered it different. I made my carbon 1 negative, so I could just kind of flip this here. Again, that doesn't really matter. That's getting more like specific, just kind of showing that carbon 1 here is what bonded to the electrophile. And then I'm representing that here by putting the negative charge in carbon 1. But again, that's just like something that I wanted to say, like clear up really quickly in case you're wondering why the numbering was off. But with this then, I know that right now it must have been a CO double bond or an epoxide. Right now, because I see this new addition here, having that single connection toward this carbon, and this carbon I circle in blue is directly connected to the O. You might have remembered there was like a slide I made that was talking about how, depending on if you're attacking carbonyls or epoxides, for carbonyls, you're always going to have one carbon. I'm gonna write it here. You'll have one carbon in between your new group and your OH bond For an epoxide, that's going to have 2 carbons, just because you have the 2 carbons here in your epoxide. Well, here there's only 1 carbon in your like CO double bonds. So that will track then in your products where you're going to see that pattern where, okay, if I have 1 carbon in a CO double bond, I'll have 1 carbon in between my organometallic here, those 2 carbons, and my OH. And you can see that by what I circled in blue. That is the 1 carbon I'm talking about here. So, kind of continuing on with the epoxide thing, we'll see that actually, I think the next one coincidentally deals with that. So, I'll save that for later, but just continuing on with this. So, I know this must have been a carbonyl that I attacked by this connection pattern that I identified in the product. This bond here that we made just has a single carbon that directly goes to the O. So there's just that 1 carbon in between the OH and this new group here. So if I draw what this could have started out as, I'm going to keep the 2 carbons here on the left. I'll draw those out. And then those would just directly be connected to my double bond here. And I'll number those as well. I'm going to say like, I'll say 3, 4. Just to separate them from this 1 and 2. I don't want to confuse those together. So I'll say 3, 4 here. And then, I guess, you know, I'll say 3, 4, 5 like this. Again, this doesn't really matter much. I'm just trying to show that I'm tracking the correct number of carbons. The numbering's just weird because I numbered these as 1 and 2, and like I said, I don't want to confuse the numbering of our organometallic nucleophile to what we started with. So these 3 carbons track with these 3 carbons here. I know, like I said, that I needed this CO double bond, so I'm just going to add that in there. And the reason I have nothing on this side over here is because I don't see any other carbons coming off of this before we started. Like I said, this is the new group we added here. I'll say this was the nucleophile here. So that wasn't there to begin with on our electrophile. So everything else on the other half of that blue bond I highlighted, that's what you draw down for this. And again, just remembering that it needs to be a carbonyl because that is what our organometallic would have attacked in order to have this connection pattern where our nucleophile and our OH just have that 1 carbon in between them. This whole like pattern kind of shifts to the whole idea with 2 carbons being in between for this third reaction. So coincidentally, this is the exact same nucleophile that we had for this one right here. Just a different counter ion. This would be like your Grignard down here, and this is your organolithium. Those are just like, it's kind of just like chemistry jargon for the counter ions. What we really, really want to look at is the R group coming off of that, which is exactly the same, coincidentally. We both have these 2 carbons here. So, now looking at our connection patterns, I again want to find somewhere on this molecule where I see 2 carbons aligned like this, just one next to the other. You will see like 2 carbons here, but you can kind of see off to the left you have this extra one coming off here. So if this was added, like let's pretend for a second that this was the new bond here. I'll say like, pretend this is the new bond. That really wouldn't make sense because then our organometallic should have started out with 3 carbons in order to make that type of connection. So we know that side won't work based on that like connection pattern there. So we have to try something else. So if we look at the other side, yes, right now we have 3 carbons coming off of this, but because we know we're only dealing with 2 in a straight line, we're going to just be forced to pretend this is the new connection here and say that this is the new bond we formed. And like I did before, we can then identify what carbon we connected to. So then this new bond here would be made to this new carbon in our electrophile that we're going to have to draw. So now that I see that where I added my nucleophile, I'll kind of box that off again. This would be my nucleophile here. Oh, I forgot about this box too, but I'll go back to that when I'm done with this. So that would be our nucleophile there. I identified my new connection. I guess you could say, like, split this up into steps. We identified where the nucleophile is. That's, like, step 1. We kind of just labeled that new sigma bond that we made to form that new connection from the nucleophile to the electrophile. And then I just did this, again, this blue circle to show what carbon we attacked on our electrophile starting material before this reaction even occurred. So I see that I attacked there just by that where that blue highlight I put is. So now this is going to come into account of seeing how many carbons are in between the nucleophile and the OH on our electrophile. So if we kind of just go ahead and count that, you can kind of see that now we have the one we already identified here. And then to the left of that, if we keep going, we have another one here. So this is how many carbons then we have in between this OH and our nucleophile I sectioned off here. So this is a really good candidate then to be an epoxide that we opened as our electrophile. Just because we see those 2 carbons here that could have been our epoxide to begin with. So if I kind of just like go ahead and like see where that gets me, I'm going to draw these 3 carbons here and connect that to this like base I have here. I know I must have started with these 2 carbons as the epoxide base carbons, and then I'll just draw everything I have coming off of that. And again, the only reason I'm not drawing this blue highlight bond in the nucleophile is because that was formed after the reaction took place. So if I go like this, let me do that again. So now these are the 5 carbons I know I have right here. And now I have to think if these 2 carbons were my epoxide carbons when I did this reaction, that kind of, oh my god, why am I losing my voice? That kind of outlines where my epoxide could have been. Those would have been the epoxide, like 2 epoxide carbons forming that bottom of that triangle. So my epoxide must be here. I'm going to make that a little smaller. And not blue. So that must be where my epoxide was. And to just like make sure we're on the right track, if we went ahead with this 2 carbon organometallic nucleophile and attacked this, it's a basic reaction. I don't see any acids in solution. In general, whenever you have like a negative molecule, you know it's going to be a basic epoxide opening type of situation. So I know then I'd attack the least substituted side. And again, this is not necessary for this problem, but if you want to double check that you're right. It's always like a good, idea too. So if I went ahead with this nucleophile, I would attack that least substituted carbon, break this CO bond here open, and what I'd end up with is this here. Everything on my left would be the same. My O would kind of swing over to this carbon here. I'm going to label them so you kind of keep track of that. That carbon there would have my OH, assuming an acidic workup happened, which usually is always the case. Axelson will always have you assume those. And And then my other carbon would be here of my epoxide. What was previously my epoxide, I should say. And now this 2-carbon nucleophile here would form a new bond. What I'm drawing right now as I'm talking is the new bond to those 2 carbons there. I want to make those blue. So then, again, that is my nucleophile, those 2 carbons there, and then this would be my new bond. So it looks exactly like what we get in our product. So really the whole idea with this is just see, like, don't even, I mean, yeah, it's important to look at what we have for our organometallic, but where this really gets going and where we can really start determining what's going on is by identifying where those organometallic carbons are. From there, then, you can just highlight that new sigma bond connection to what would be our electrophile that we're about to draw. And then all these blue carbons I circled here, I did that to represent the number of carbons in between that O and the new nucleophile we attached. Because then that identification would help you identify, okay, was this a carbonyl I started with or an epoxide? And then from there, of course, we just did, we kind of work backwards to determine what we started with for this electrophile section. And then I kind of left this out for the mechanism section. If I wanted to go ahead and say what kind of additions these were, this technically, for this box here, this middle row, this middle row, because we can number the carbonyl as like starting at the O. This is also something that, like, I feel like it wasn't explicitly mentioned until we did the addition to enone type of thing. Usually we say this would be an addition, but now that we have the extra terminology to say a 1,2 addition, that would be more specific, so we would just for this say 1,2 addition, because we're adding at that carbonyl carbon. This is like what we've done before, where the nucleophile goes ahead and attacks at that partially positive carbonyl carbon. So we've seen stuff like this before, it's just now we're adding this new term because we have it in our word bank, I guess. But for the last one, this, although it's similar to what we've done before, we're attacking the carbon connected to a electronegative oxygen, at least in the case for these 2 we did. This, instead of being considered our addition, for this, because epoxide opening, yes, we're adding something, but because epoxide opening occurs in an SN2 mechanism, that is the best option for this. But yeah, it would be best for this, just say SN2. The addition, whether it's 1 and 4 or 1,2, is just best reserved for a carbonyl or an entire enone. So that would be this problem. I'm actually, I have your email open right now. Which was the other one? Let me see. So, honestly, I'm just going to go through this entire next page. I might as well. Let's be real. Also, these are kind of fun. I'm sorry. That's probably terrible to hear the night before the exam. Someone saying this is fun. But, so looking at this, I'll start with A. So, again, too, if you already, know, A or something, just skip ahead until I get, to B or something. But for NaBH4, I'm just going to make this as thorough as possible. This would be one of our hydride reduction reagents. remember that reductions fall under two categories. We actually just dealt with organometallic reductions in the entire other page. In this case, this would be dealing with the hydride ones, so we could have organometallics, or we can have the hydrides, or these. In this case, we're dealing with the hydrides. Of course, like the two of these are LiAlH4 and then NaBH4. So the main differences between, LiAlH4 and NaBH4 is that with NaBH4, this is only going to attack your aldehydes and ketones. LiAlH4 would literally attack every single thing possible, and what I mean by that is it would attack absolutely any carbonyl. It would attack aldehydes, ketones, esters, carboxylic acid, and it would open epoxides, and it would do SN2 with any leaving group or sulfonate ester, which is also just another leaving group. I have this written down on one of my slides. I'll spare you me writing it out again, just because that might take time and add to the video. But NaBH4, it's going to be selective for those aldehydes and ketones. So, and I noticed you did this in your work, but this would be our carboxylic acid. And we could think, all right, is this going to be touched by NaBH4? Well, no, right? Because we're only going to attack those aldehydes and ketones. So I see two ketones here. I'll say ketones. So everything in this product in this box will be exactly the same that we see in our starting material. The only thing that's going to change is the fact that these ketones, one of those O bonds will break when we attack here with the H-. Again, you do not have to do the arrows. Just for a visual, I might as well. So that would attack at the carbonyl carbon. You could think of this, I guess, for the chemistry terms. This would be a 1-2 addition that would open this up or break that pi bond, and then you'd be left with the single bonded oxygen. And then she mentioned just assume acidic workups. So that single bonded oxygen would be protonated into just an OH. And again, the same thing for the other one too. So that's what we would get there. For the next one, for B, right now it looks like we have no idea what's going on, but that's okay because we could just identify what exactly is changing. So I see right on my left side, I have an aldehyde here. I have a secondary alcohol and a primary alcohol. In our product, it looks like the aldehyde stayed completely the same. I don't see anything changing about that. But what I do see is the alcohols became carbonyls. If you want to be more specific, you could say ketone and aldehyde. And this kind of just goes back to memorization, unfortunately. But for our oxidations, we have the options of doing PCC, Jones, or Tollens. Someone mentioned, I don't know if it was you who mentioned this, but someone said for Tollens they didn't know what exactly the difference was between this and the other, reagent options. Tollens will only convert aldehydes to carboxylic acids, and that's the only thing it would do. So actually, if we said Tollens was the reaction or the reagent for this, the alcohols would stay there in the product, but we would see this aldehyde become a carboxylic acid. So it would look like a carboxylic acid with two alcohols connected to it. That would be if we used Tollens. But with Jones, if we did use Jones for this, we would end up getting everything we see here, at least at the ends of the molecules, we would get this aldehyde and this primary alcohol to go all the way and be super oxidized to two carboxylic acids here. The ketone would just stay the same. It's kind of blocked. It's like roadblocked right now by two carbons, so those couldn't become OHs or anything to be considered a carboxylic acid. So this means that we're just left with PCC. If you just see a primary or a secondary alcohol going to carbonyls, you know that it must have been PCC. So we can say CrO3HCl and pyridine. For this one, I mentioned in the email I sent that whenever we're dealing with NaH, this is always going to be one of your really strong bases. This will only act as a base. It's actually, it's honestly one of the strongest you can have. It's going to rip any proton that is acidic. In this case, when I say acidic, I mean like connected to an electronegative atom. So like OH or NH, those would be acidic. In this case, you could see we have that OH. That's one of our acidic protons. So this H here, again, you don't need to show arrow pushing, but just for the visual, this H would grab this proton, and pretending there's like a bond right now between this O and H, those electrons would be sent back to the O to make that negative. So what we would end up getting would be something that looks like this. Let me go like that. So just be O minus with its 3 lone pairs. So previously, before we deprotonated that was a very poor nucleophile weak base. That would be in like the lower right quadrant of the nucleophile chart. So I'm going to write that too. What we had before was right here. That would be like poor new weak base. Now that we deprotonated this thing with NaH, now it is going to be all the way up here. So now this thing is going to be classified as a good new strong base. So we went from something that can barely do anything to something that's going to be extremely reactive. So if I have this good nucleophile strong base right here, I know that that's going to want to react with any sort of like leaving group to do either like SN2 or E2 or some mechanism like that. So if I look to my right side of the molecule, what I'm noticing is I actually do have a good leaving group right here. My chlorine is just considered a good leaving group connected to this alpha carbon we see to its left. So if we have this good nucleophile strong base on our left side of the molecule, what's going to end up happening is combining this with a primary unhindered alpha carbon, the mechanism we'll end up getting is going to be SN2. So what we'll see is one of these lone pairs will attack the back side of the chlorine and kick the chlorine off. And what we'll be left with is a ring. So when I'm doing this, the first thing you should really just do is number your carbons. So I'm going to do that. I'll just do it in blue. So when I'm doing this too, because I'm forming a ring, think for a second, is this oxygen going to be in that ring? Like it's connecting to a carbon. So ultimately, at the end of the day, when we draw this ring, the O will end up being in there somewhere. So I'm going to also count the O as being part of this like ring I'm going to number. So I'm going to say the O is 1 and just go down the line till I hit this carbon I connected to. So 1, 2, 3, 4, and 5. So my product right now is going to be a 5-member ring. So I'm just going to go ahead and draw that really quick. And I'm going to number it too, just so we could keep track of like what exactly is going on. You could start numbering it anywhere. It doesn't really matter as long as the connections are correct to these numbers here. So I see that on... Oh, wait, also I should literally... Okay, one of these carbons should be an O. In this case, I said carbon 1 was our O. So I'm just going to change that to an O right here. And that would be our 1. So now I'm just going to follow the rest of the connections. So I see that carbon 2 has this ethyl group here, so I'm going to draw that in. I also see that carbon 3 has a methyl, so I'll just put that there as well. Obviously my chlorine left, that's not even in the picture anymore. So this is what you would get as your answer, actually. This is what you'd be done from this point on. So then for D, this one is going to be kind of more involved, but it kind of ends up being fun. Like, I don't know. So it's dealing with this. The first thing, I mentioned this in the email, the first thing I noticed looking at this is that my ethyl here is not in the same spot. And the reason this is a problem is because now we can't compare the OH to the CN and what exactly changed or whether it changed in terms of like wedge and dash to see what this reagent should be. So, having that in mind, I want to get this product so that this ethyl is down. Actually, I think I said down in the plane in the email. It's going to be up in the plane here. In when we like end up turning this thing to try to match these two together. So I'm gonna just go ahead and do it so you could see what I'm exactly talking about. You could do this totally in your head. I'll do a Newman projection really quick so we can kind of see why exactly I'm doing this or like what's going on. So if we pretend I'm looking down this bond here, straight down that one. I won't do the back carbon when I draw this, just because we're going to be focusing on what's going on with the front one. I'm going to do it right here. So when I draw this Newman projection, I know I want to end up where, like on this side, my ethyl is up. I'm gonna draw first what we want. So my ethyl would be up. My implied H in here would be wedged. So I'll put that as the wedge on this side. And then I won't say like CN or OH. I'll just say my like, actually I'll go like this. We know that the OH or CN, depending on what we're looking at, should be like generally in this down dash spot here. So I want to try to get this Newman projection I'm about to draw to look like the one I just wrote out here. So when I make this Newman projection looking down this bond here, what I'm going to get is the CN is going to be pointing straight up. The ethyl is wedged down, and my hydrogen is dashed down. So now to get this here look like this one, it looks like if we did a turn this way, a 120-degree turn to our left, counterclockwise, this looks like it will overlay with the starting materials Newman projection that we just drew out previously. So I'm going to go ahead and do that. Also, I'm going to make this smaller and put it here. So if I turned that Newman projection, I'd get exactly what we want, which is the ethyl would be up. My CN would go to the H spot. And the H, of course, would just shift over straight to the right. So now, when I redraw this, I'd end up getting, coming off of this carbon here, I'm going to highlight it. I would get my H being wedged, the CN would be dashed, and then my ethyl would be up in the plane. So now that I've dial turned around this bond here, now I can accurately, that is a terrible arrow, oh my god. Now I can accurately compare the wedges and dashes I see on the product to the ones on the starting material. And I'll go ahead and make the H implied there as wedged, just so we can see the bigger picture. So I'm comparing these two things. So what we can kind of see right now is that OH was dashed to begin with. What we would end up working with. We know we're going to make this OH into something better that can actually leave. Right now, I'm going to say this in a second, but right now we know it's a terrible leaving group. In the product, that OH eventually somehow will end up doing that, like I said, but that OH somehow went to a CN, but it's also dashed. So since we have retention overall, this is going to come into play with what this step could have possibly been. So I'm going to go ahead and continue just working with what we just did and seeing how this will all come together, because it really is like putting a puzzle together, if I'm being honest. So right now, I know that this step here, NaCN, was the second step to get to the product we see that we're given. So what I know about NaCN is that CN minus, or let me write that here. This is a good nucleophile, but a weak base. And then what I also notice is that this nucleophile, our final product, or even the starting material, whatever you want to look at in this case, these are secondary carbons here. There's only two other carbons that we're connected to. And if I combine, I know we don't know the intermediate yet, but it's fair game to assume that because these are both secondary here, the intermediate must have also been secondary. We likely didn't change the number of carbons coming off of this central carbon I'm highlighting, or just the entire molecule in general. So I know that that secondary spot must have stayed secondary. All we're changing really in this reaction is what's coming off of that carbon. We're not changing like the substitution of the carbon itself. So keeping that in mind, if I combine this good nucleophile weak base with this secondary electrophile, what mechanism would happen? And the answer to that is SN2. But then it's also important to keep into account that SN2 results in inversion. So this is interesting because then I know, comparing the starting material to the final product, they both stayed dash. So you think retention, but this second to last step here by nature does inversion because it's an SN2 step with that nucleophile. So what this means then is this step here, this first step, must have also been inversion. And I think I said this in the email I sent to where I said something about two inversions would kind of like cancel each other out and result in retention overall. This is what I mean. So flipping something once and then flipping it back to where you started, basically. So if you wanted to think like RNS, again, I wouldn't use this often because sometimes it kind of breaks down as being like a really, really good tool to use. It can get tricky. But if, just for the analogy, if you're thinking RNS, This here would be R. You'd switch it or invert it to S and then back to R again. So then you start with R and end with R. So it's kind of, canceling itself out. I always think of like two negatives. So two inversions in this case would cancel out and make a positive, which would be a retention. So it's kind of like inversion plus inversion. Overall, that would be like a retention. However you want to think of it is totally cool, but the fact that we were able to work backwards to determine the rest of the reaction and just putting this puzzle together is super, super helpful to finishing this entire problem right here. So I know right now, I was saying this in the beginning, the OH is such a terrible leaving group. We need to make this into something that we can actually work with and something that is actually reactive. So the best way to do that without changing where this reactive spot is right here, that spot I highlighted, the best way to do that would be alcohol activation. And specifically the ones that do inversion. So our options for this are the SOCl2 pyridine, and then we can do PBr3, or we can do PCl3. So whichever one of these you want, it's totally cool. I'll just choose PBr3 for now, but it could be any one of those in this box. So then once we do this, what we get at the end would be almost like the exact same thing, except now this secondary carbon here would have our leaving group, the Br, as wedged, and the H would instead be dashed. And of course, it never hurts. I was going to say it doesn't always hurt. It never hurts to number your carbons. So I won't number that ring just because it's kind of obvious it's there. So we have the 4 carbons we need. So we know that this must be our intermediate product. And of course, like I was saying before, when I guessed that, okay, this must be secondary here at that alpha carbon in order to go through this whole mechanism and keep everything looking the way it did in the final product, we can see then that it in fact was a secondary electrophile leaving group that we formed. So it really is like putting a puzzle together, but overall, identifying what changed between your final product and starting material, using that knowledge of what you observe, whether it's like an inversion or a tension, to then work backwards, see what you're given and how that would change what your intermediate is to your final product. And then from there, knowing like the type of nucleophile that is and secondary electrophile, or just in general, the reaction or the mechanism that would happen here would then again let you determine whether it's inversion or a tension. Just for example here, we knew this whole thing together would be SN2, so that would be an inversion. And then putting that all together with what we did before, we know that this must also be an inversion as well to retain that stereochemistry overall. When in doubt, I really, really suggest just writing everything out because this stuff can kind of get crazy. So oftentimes, I think I did this on my exams too, there would be like an entire list off to the side where I just had my observations listed out and written down. So that never hurts. Honestly, it's probably the best possible thing you can do. But yeah, that's how you do these problems basically.